That's a very specific. Well, I like this question because for a general question, I can just be brave, have courage, you should be curious, and you win. Okay, so the recording is okay. So we have 22nd March, have math for economists lecture. Okay, I don't remember the number. Okay, the question. What should we do? How we go back to the original problem? How to go back from dual to the from the dual to the original problem. Problem in the case of infinitely many solutions. Okay, in the case of infinitely many solutions. That's right. I got your question right. Yeah.
Absolutely.
Okay. So let's do it on. So I will work on the example. It's better. I can just discuss something, but I think let's do it on an example. So I will invent the numbers. Just let's pretend that we have a minimization problem, something like 5x1 plus 3x2 plus 5x3. What do I need? I need something like x1 plus x2 is greater than 1. Boom, 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 minus x1 plus 2x2 plus x3 is greater than 2. x1, x2, x3 are greater than 0. So let's solve this problem. If I'm not mistaken, we will have exactly the case you wish. But if not, I will correct one number, maybe because I try to invent something from scratch. So maybe I have done some mistakes in creating the problem, but I think that's okay. Okay, first, what do I see? I see that I have 3 variables. Oh, 3 variables, I'm scared. So I go to dual. So that's okay. We have started solution. Yeah, we have already started solution. Okay, that's original problem. I see that it is in a standard minimization problem. So I check. So what should I check? I check that it is a standard minimization problem. I see that I'm minimizing something C transpose X, given that AX is greater than B, all X1, X2, X3 are non-negative, so it's standard minimization. So when I go to dual, I create maximization B transposed, I don't know, some other variable, that would be Y, subject to A transposed I is is less or equal to C, and all variables are non-negative. Okay, in my case, I have a problem. Yeah, I have 1, 2, and 1, 2 there. So yeah, can you see how I have created a problem? Yeah, I have. So maybe you see already that I have 1, 2 there and 1, 2 there. So that's exactly your case. That should be, if I'm not mistaken, with other 2 inequalities. So I maximize. So y1 will correspond to first inequality, y2 will correspond to the second inequality, and basically I will maximize 1y1 plus 2y2. Then I will write this matrix transposed, subject to all variables y1 is non-negative, y2 is non-negative, and oops, let me move on to the next page because it's the end of the page. So it's better to start with a lot of space. So I will just copy all I have invented. 5, 3, 5, 1, 1, 0, minus 1, 2, 1, and right hand side is 1, 2. Okay, I have a problem to maximize choosing y1 and y2. I have copied everything. So I need to maximize 1y1 plus 2y2, subject to y1 is non-negative, y2 is non-negative. 5, 3, 5. And then I have 1y1 minus 1y2 is less than 5. 1y1 plus 2y2 is less than 3. And 0y1 plus, if I'm not mistaken, 1y2 is less than 5. Everything is fine with dual. So first checkpoint. Are you okay with going back with creating a dual problem? Okay, now what's the advantage of the dual problem? The only advantage is that we can solve it graphically. That's a huge advantage. We can solve it graphically. Okay, let's draw all the constraints. We work in a first quadrant. It is y1, it is y2. So I have 3 lines, line 1, line 2, line 3. They correspond, basically, the corresponding variables will be x1, x2, and x3. And basically, yeah, let's work. So let's draw all the constraints. So what can I do? The first one is 5 and minus 5. The first one is line 1, y1, y2. If y1 is 0, then y2 is minus 5. If y2 is 0, then y1 is 5. Okay, I draw this line. I have 5 minus 5. Oops, that's the line 1. Okay, then I go on with line 2. Line 2, y1, y0, y2. I have 0, 0, and it will be 1.5 and 3. And that's 3, that's 1.5. I have line 2. And basically, I have line 3. Line 3 is a horizontal line. That's line 3. Basically, I have drawn all the lines. Now I just will fill the feasible set. What is a feasible set? The set of all possible y1 and y2. So it's better to just check using test points. So I take 1 point, and the whole region of that point should either be feasible or non-feasible. So I use test points. So the easiest test point is a point 0, 0. I check test point 0, 0. I look at my inequality 0, 0 satisfies the first inequality, 0, 0 satisfies the second inequality, 0, 0 satisfies the third inequality. So the whole region of a test point is okay. Okay, I feel yeah, that's fine. That is my set. And then I need to optimize what I'm optimizing. I need to maximize what I'm maximizing. I forgot. I'm maximizing y1 plus 2y2. y1 plus 2y2. So if I draw the level curves, let me draw them in blue. y1 plus 2y2 is equal to c. Okay, and y2 is equal to c over 2 minus 1 over 2 y1. So if I draw these level curves for different values of c, I will obtain the curves like that. This is the first level curve, the second level curve, the third level curve. I can draw a lot of level curves. And basically, I'd like to increase c because I'm maximizing the value. And so I'm moving my level curves in the right north direction. And basically, the last moment when my moving line, my level curve, will touch the feasible set, the shaded feasible set, the last moment will be when we will have a full segment of optimal points. The last moment, this line will, it's difficult to draw coinciding lines, but I will do my best. So this is the last moment, the biggest value of C, which creates a situation when a level curve touches the feasible set. Okay, and this segment will be the set of optimal points. So I have infinite number of optimal points, the whole segment. Let's call these points A, B. So I have solved the dual problem, not the original one. The dual one I have solved. So the answer for the dual answer. The whole segment from A to B is maximum point. No, point is the optimizer. Yeah, the optimizer. How to write it? So I may say how to, if I need to write the answer. So let's find the maximal value. I understand that the maximal value is equal on every point of this segment. So to obtain the maximal value, I need to plug in any point. So maximum is equal to, let's plug in the point A, for example, or we may plug in the point B. Yeah, the maximum is A has coordinates 0, 1.5. B has coordinates 3, 0. And the maximum, I may plug in A, I may plug in B, I may plug in any point in between. And I get basically 0 plus 2.5, I get 3. Okay, so we have solved the dual problem. And now we need to go back to the original problem. Yeah, are we ready? Any questions?
Ready, yeah.
Yeah, let's go.
Okay, let's go back to the original question. Basically, we have one rule that can be stated as two rules, but basically we have one big rule. Let me write it in big letters. Lambda times dl d lambda is 0. That's the main equation from first order condition, from the theorem we have stated. many times.
You wrote DL over DL.
Yeah. I wrote nonsense. Yeah, you're right. It was a mistake. Yeah, you're right. Okay, that's the main rule. Or so either of them, so one of them, at least one of them should be zero. Either lambda, either DL lambda, either both. But that cannot be that both of them are not equal to zero. And we remember that y is Lagrange multiplier. Y is a Lagrange multiplier for corresponding inequality about x1, x3, and xi is a Lagrange multiplier for the corresponding inequality about y1 and y2. So basically, we can use this rule twice. We can use these rules thinking of lambda as x, meaning dl d lambda is a corresponding inequality about y, and lambda is y, and dl d lambda is treating as an inequality about x. Okay, so basically, this general rule transforms to
Boris, I'm sorry. May you swipe, please, just for a second? Yes.
Yeah. If I need to.
Yeah, that's enough. Thank you very much.
So my main position that with online lectures, it's much harder for me and for you to communicate with a big whiteboard. I can write here, leave something important on it. Yeah. If you need something, then don't be shy. Okay, and this rule basically can be stated as two very specific rules. So first one, if a y is positive, I don't care which one, y1, y2. If y is positive, then I should have zero. So the corresponding inequality about, well, let's write like this: the corresponding x inequality should be active. And the other rule, if an y inequality is non-active, then the corresponding x should be zero. So I have two rules. I cannot have two non-zero multipliers in this equation. And basically I have two rules. If y is positive, then the corresponding x inequality should be active. If y inequality is non-active, then the corresponding xy should be zero. Okay, and now I use these two rules. And once again, I always should add that there is a good way to avoid listening to my lectures. So you can always open Ferguson about linear programming. It's a marvelous book which is pretty well written with a lot of examples, and that's important to have examples in math. Okay, let's go on. So the problem in my case that I have a whole segment. I have a whole segment from A to B. So my optimal y, my extremis, are the whole segment from A to B. So basically, I need to consider cases. What should I do if I have infinitely many solutions? Then I will consider cases. What to do? That may be boring, but I have no other option. Okay, so I will consider three cases. A, interval from A to B with endpoints excluded. So in my problem, in the optimization result, I have included endpoint. I will consider three cases. Case 1, case 2 from A to B excluding A and B, and case 3, point B. And I will go back to the original problem in all three cases. That's boring, but I cannot provide a better, honest solution. Yeah, sometimes we may, let's say, trick and say, oh, it's a very, very complex problem. Let's bet that the organizers of exam have considered the case when have created such an exam when all cases will coincide, but that's not a tricky method. So the honest method is to consider all the cases. Okay, case A. Let me draw all. I have, this is L. Sorry, I have a line here. I have a line there. This is line 3. This is line 1. This is line 2, as far as I remember. So let's consider case 1. Case 1. Point A. Y1 is 0. Y2 is positive. What should I add? A does not belong to L1. A does belong to L2. A does not belong to L3. Okay, so I'm just checking which inequality is active, which Y is positive. So using this rule, these two rules, I understand that, oh, I'm happy to see non-active inequalities. That's the most beautiful thing we can have. Yeah, that means that x1 is 0. I don't know about x2, no information. Maybe it's 0, maybe it's not 0. We have no information. And as inequality number 3 is not active, if inequality is non-active, then the corresponding x is 0. x3 is 0. Okay, y2 is positive. I may conclusion that x inequality number 2 is active. Okay, let's recall what is x inequality number 2. X inequality number 2, as far as I remember, it was, let me see my notes, x inequality number 2. X inequality number 2, it was minus x1 plus 2x2 plus x3, and it should be equal to 2. Okay.
Yes.
And finally, I have, yeah, thank you for action. I appreciate very much when you are active. Okay, I plug in 0, 0, I have minus 0 plus 2x2 plus 0 equals 2, x2 is 1. Oh, I have solved the case A. Let's move on. Case A, we go back to the original problem. X1 is 0, x2 is 1, x3 is 0.
Борисович, can I ask you?
Yeah.
Maybe I forgot something, but could you please return to the previous page? So if it happens so that we would have that point A belongs to line 3 and doesn't belong to L1 and L2, which constraint would we then use? So here we saw that A didn't belong to line 3, didn't belong to line 1, so we used the inequality number 2. But if it belonged to
why I I have another reasoning. No, it's a trap. Be careful. To use inequality number 2, I pay attention to that y2 is positive.
now I remember that. Yeah, y2 is just like a lambda for this constraint.
Yeah,
Yes.
from
yes.
these from A1, sorry, from A belongs to L1, I make conclusion that x1 is 0. From inequalities, I make conclusion about 0 or not 0 the corresponding x is. From active, non-negative, from positiveness of y, I make conclusion about active, non-active inequalities, x inequalities. Okay.
Yeah, right. Now I understand clearly. Yeah, thank you.
Yeah. So
yeah,
basically, I check whether the variable is positive, and I make conclusion about whether the corresponding inequality is active, non-active. I check whether y inequality is active, non-active, and I make conclusion about whether the corresponding x is 0. Okay. So the number, even you've spotted the problem exactly. So the number is different. Yeah, I have 3 inequalities for y1, y2, so for y1, y2, but I have only 2 inequalities for x. So I cannot match inequalities. I can match inequalities and variables. Okay. So let's move on to the case from A to B. Excluding endpoints. So I haven't excluded endpoints. So be careful. This point is excluded. That point is excluded. So I conclude that y1 is strictly positive. y2 is strictly positive if I consider the segment. Oh, sorry, not the segment, but an interval. So I see that both y1 and y2 are positive. I have lines like there. So this is L3, this is L1, that is L2. A belongs to L2. L does not belong to L1. L belongs to L2. Sorry, A belongs to L2. A does not belong to L3. What is the conclusion?
Well, probably not A, but AB.
Yeah. It's not A. So it's like.
Conclusion is that x2 is 1.
Oh, it's better like this.
Boris, I
you're
have
right.
a question. Is there any possibility that we consider not just the cases, but the graph itself and say that, well, L1 and L3 are like, in each case, the solution does not belong to L1 and L3. So
yes.
For any cases, it's only the case when x1 and x3 are 0 and x2 is 1, and that's it.
Yeah. In that case, in our particular example, you are right, but I should warn you. So I have created an example just.
Okay, yeah, I get the idea. Yes,
so,
it's just doing the general stuff, not for
in
this.
that case, you are completely right. We can avoid considering all these cases. We can just say, oh, it's obvious that in all cases the situation will be the same, because it's hard to invent something tricky from scratch. So if you write the question, I don't think 1 day or 2 days before, then I can invent something tricky. But when I try to invent something from my head, it can happen to be too simple or too hard. Yeah, when it's hard to invent something that is at the level of difficulty, affordable but hard. Okay, in that case, you're right. Yeah. So yeah, let me write with the same, better to avoid new rules. So I will write x belongs to an interval, so from A to B. So x does not belong to L1, x belongs to L2, x does not belong to L3, and I have x inequality number 1 is active, x inequality number 2 is active, x1 is 0, x2 I don't know, x3 is 0. And basically you are right, I will obtain the same solution there, because I will have, using that one, I'll get that minus 0 plus 2 times x2 plus 0 is equal to 2, x2 is 1. And basically, if I consider the case B, so I have dual, I have original, I have y1 is strictly greater than 0, y2 is 0, B belongs to only to L2, and B does not belong to L3, L1. So I make conclusion that x1 is 0, x2 I don't know, x3 is 0, and the inequality, x inequality number 1 is active. I don't know about x inequality number 2, so I cannot make any conclusions. And basically, the first inequality was x1 plus x2 is 1. I plug in x1, and I get x2 equal to 1. So basically, the answer for all cases, I have x1 equal to 0, x2 equal to 1, x3 equal to 0, and minimum is 3, as far as I remember. It's exactly the same. But in another example, we may obtain, so we need to consider cases one by one. There may be some subtleties. Okay, so it took us a little bit long, but that's okay. We have enough of time to answer all your questions. Okay, I'd like to
thank you.
Clear at every point. Oh, we have 20 minutes. That's a little bit. Okay, so that's a little bit.
40 minutes, not 20, 40.
40?
Yes.
40 minutes.
Yes,
am I
it
brave
is
enough? Yeah, 40 minutes, yeah, not 20. Okay, am I brave enough to start? Okay, so it took us a little bit long. Okay, let's just solve some more examples. So today, no new theory. So next time we will cover duality in general. But today, let's relax and solve some. Let's relax. Yeah, because I don't like to be in a rush, in a hurry with general duality, because it's hard enough to get the idea of moving envelopes, to work with some iterative examples. So let's relax a little bit. So I will not cover what I have planned today, but that's okay. We have enough to solve home assignments, to relax and prepare a little bit for exam. I will just open some hard path problems on optimization, and let's do that. Okay, let's do like this. Okay, and I will go something like that's too easy, that's too easy. Ooh, everything seems easy to me, but let's okay, let's provide the following example, maybe. Example. Ooh. Okay, oh, yeah, let's solve that one, maybe. That's exam 2013, and we have monopoly. We have monopoly, and the revenue, total revenue, is given by the formula 6x minus x squared plus y minus y squared. We have two product monopoly, two product firm, and x and y are outputs. X, y are outputs, and the total costs are given by x squared plus y squared plus 4x plus 3y, and we need to maximize total revenue minus total cost by choosing x and y, but we have a condition. That that's a little bit strange, but okay, let's do like that. Subject to the constraint that profit should be non-negative. That's a little, and x and y are non-negative. X is non-negative, y is non-negative. Okay. That's more. The statement of the problem is clear. Can we go to the solution?
I think yes. I think it's absolutely clear.
Yeah.
For me, it's a little bit strange to maximize given this constraint. I honestly don't understand a little bit the logic behind, but it's a problem. So I also wish.
Well, like it's a bit not non-standard form for us because we always had like two constraints that were kind of different from the maximization function, but I think it won't change anything really.
Okay, let's move on. So from mathematical viewpoint, everything is perfect. I have function to maximize. I have constraints. I don't care about the meaning. Honestly, I don't. I understand. Okay, well, so I have a function. I have constraints. Let's use Kuhn-Tucker theorem. Okay. So from mathematical viewpoint, everything is here. I may forget about monopoly, firm, and so on, because everything is stated as a purely mathematical problem. So I will ignore the meaning of xy, of xy. So okay. So basically, what we need to do, we need to check non-degenerate constraint qualification problem. Okay. So let's check. So let's simplify a little bit. Let's simplify. Our profit phi will be 6x minus x squared plus y minus y squared minus x squared plus y squared plus 4x plus 3y. It will be it will be it will be 2x minus 2x squared minus 2y minus 2y squared. So it will be my profit. Okay. So let's check non-degenerate constraint qualification. I have basically three inequalities. Yeah. I have so our procedure will be the following: in DCQ, Lagrangian function, first order conditions, and sufficiency. Okay. So first in DCQ, I have three constraints: x greater than 0, y greater than 0, and 2x minus 2x squared minus 2y minus 2y squared greater than 0. Okay, I have three constraints. When I'm doing in DCQ with inequalities, I should check every possible combination. So it's not the case, it's not the equality case. I'm checking all combinations. So I have first, second, third. So I check all the possible combinations. Only first, the Jacobian matrix is 1, 0. Only second, Jacobian matrix is 0, 1. Only third, the Jacobian matrix is the derivative with respect to x is 2 minus 4x. With respect to y is minus 2 minus 4y. First plus second, the Jacobian matrix is 1, 0, 0, 1. First plus third. Woo, that's a lot of cases, but I'm brave enough. Be brave, be careful. You will win. Okay, 0, 1, 2 minus 4x minus 2 minus 4y. Ooh, what should 2 plus 3. 2 plus 3 is 0, 1, 2 minus 4x minus 2 minus 4y. And basically all the inequalities, 1 plus 2 plus 3. Okay, let's check all these cases. So are there, in the first case, any dependent rows? If I have only one row, 1, 0, any dependent rows? No dependent rows. No dependent rows. I'm happy. The same for the second case. Ooh, here it seems at first that it may be 0. Yeah, at first it seems, why not? At first it seems, oh, it may be equal to 0 in DCQ failed. I'm scared. I should run away on the exam. No. Why? Because this happens at which point? It will happen, but it will happen at the points where x is 1 over 2 and y is minus 1 over 2. And this point is not feasible. It's prohibited by our constraint. So on my feasible set, because I'm considering whether in DCQ is satisfied or not satisfied, on my feasible set, there are no points where this matrix will have a 0, 0 row. Okay. On my feasible set, on this is feasible set, feasible set. on my feasible set, there are no points when the third line is 0. Okay, I'm happy. Okay, this is this has rank 2, so that's not a problem. This once again, this is non-negative. This is non-negative, non-zero. The element -2 - 4y is non-zero, so the rank is once again 2. This situation is not possible at all. Yeah, both inequalities. So I cannot have 3 equalities. I cannot have x equal to y, x equal to 0, y equal to 0, and 2x or they may.
No,
2x.
no, it is possible.
I don't think so. Yeah, it is. So
If everything is
Ah,
0, then constraint is satisfied.
Yeah. We need to check this point,
But
especially.
still, the rank is 2, the maximum.
But we needed a rank equal to the number of rows. The number of rows is 3, not 2.
But how is it possible?
So we have x equal to 0, y equal to 0, and 2x minus 2x squared minus 2y minus 2y squared is 0. And in this case, I have a matrix. Yeah, I have a problem, but I'm not scared. This is 2 minus 2. Yeah. And the rank is less than 3. Okay.
In any case,
Okay, let's move on. So we have a problem here. So 0, 0, it's a bad point, but we are brave enough to solve the problem. Okay, let's move on. And the last case, I think it's we have no problems in the last case, because if y is 0, then we have y is 0, and we have yeah, we cannot have so let's check the last situation. 2 and 3 have 0, 1. We have 2 minus 4x minus 2 minus 4y. And we have the second one is y equal to 0. The third one is 2x minus 2x squared plus, minus 2y minus 2y squared is 0. So y is 0. I conclude that either x is 0, either x is 1, but that's not possible, because I'm considering x greater than 0. The first one is non-active. No. In just a moment, I will answer the question in chat. I will finish. As I consider the second and the third, so first one is non-active, and hence I get x equal to 1, and the rank is 2. So in DCQ, this case is okay. And I have a question in chat: why DCQ holds? Yeah, we have a problem that this point is a bad point. In DCQ is not satisfied at that point. We have a problem, but we will deal with it. Okay, let's move on. We have a bad point, 0, 0. So what does it mean? We have a bad point. The DCQ is not satisfied at this point. What is the problem? Don't be scared. That's okay. Be brave and courageous. It means that it may be optimal even if Lagrange multiplier method. What about the 0.050? Okay, let me finish with that point. It may be optimal even if Lagrange multiplier method will not catch the point. So it may be optimal and Lagrange multiplier method may miss the point. What about the 0.50? Are you speaking, Alexander? What about this point? Are you considering which active inequalities? So if 2 and 3 are active, then they are active. If you put here 0 and you have no solution as x equal to 0.5, just plug in. So if you have 0 here, you have 2x minus 2x squared is 0. 2x minus 1 minus x is 0. So 0.5 is, yeah, I understand why you have this question. At the point 0.50, you have problems with rank. You're right. But at the point where you have problems with the rank, you don't have the third inequality active. Okay.
Boris, I'm sorry. From where did the bad point emerge? From which like case?
From this case, 1 plus 2 plus 3.
1 plus 2 plus 3?
Yeah. If I have every inequality active.
Yeah, everything is 0, yes.
Yes, everything is 0. And the rank is not 3. I have 3 active inequalities, but the rank is not 3.
But isn't it like the rank is always 2 for matrices like 3 to 2, like
yeah, you may. So, but we need to check that there are yes, the rank for matrices for 2 by 3 cannot be greater than 2. You are right, but yeah. You need to provide me a point where all 3 inequalities are active. Maybe if in another problem we have no such point, then I will just say that in DCQ hold, because this matrix obviously has a rank less than 3, but I need to provide a point where this happens. Okay. I need to consider such a matrix in a case when all inequalities are active, and maybe in another problem there are no such points. And in this problem we have a bad point. We have a point 0, 0 when we have 3 active inequalities, and yeah, and the rank is not 3. Yeah, okay. We have a point where all 3 inequalities are active, but the rank is not 3. Let's move on.
Yeah.
We have a bad point, and DCQ is violated, but we are happy. We are courageous and brave. Let's move on. Okay, now, when doing a Lagrange multiplier method, we need to remember that our Lagrange multiplier method may fail to find to catch the 0.00. Maybe the optimum is there. So you need to consider that points separately, not using Lagrange multiplier method. So we need to consider this bad point. Let's call B bad point. To consider B without Lagrange multiplier method. So maybe the maximum is in B. So when monopolist should not produce so maybe the optimum is there. Okay, let's move on. We have two versions of Lagrange multiplier method. We have a version with 3 lambdas, and we have a simplified version where we ignore non-negativity constraint. So we have two versions. I will write both, but I will solve only one of them because they are completely equivalent. We have two versions. Let's call it full one. I introducing 3 lambdas because I have 3 inequalities. So my Lagrange function will be like 2x minus 2x squared plus, sorry, minus 2y minus 2y squared plus lambda 1 times x plus lambda 2 times y plus lambda 3 times 2x minus 2x squared minus 2y minus 2y squared. Okay, that's a full version. Yeah, when I just write every, I write lambda for every inequality, but I'm too lazy. So we will write like Kuhn-Tucker version. Kuhn-Tucker, that's a full version. And the Kuhn-Tucker version. So I just ignore these non-negativity constraints. 2x minus 2x squared minus 2y minus 2y squared plus 1 unique lambda times 2x minus 2x squared minus 2y minus 2y squared. And then I write first order conditions. First order conditions are different for these two. So let's Lagrange function A, Lagrange function B. First order conditions are different. So let me write first order conditions for both functions, but I will solve only for version B. So let's write first order condition for both functions, but I will solve them only for B to simplify our calculations. Okay, what are the first order conditions? They are, if you use the first version, you will have dl dx is 0, dl dy is 0, lambda 1 times dl d lambda 1 is 0, dl times lambda 1 times dl d lambda 2. I'm lazy. dl d lambda 3 is 0, lambda 1, lambda 2, lambda 3 are greater than 0. dl d lambda 1 greater than 0, dl d lambda 2 greater than 0, dl d lambda 3 greater than 0. Yoo-hoo! That's our first order conditions for the version A. I'm too lazy to solve them. I hate having a lot of lambdas. What are the first order conditions for the case B? What will change? I will have only one lambda. So lambda dl lambda will be 0. Lambda is greater than 0. dl d lambda will be greater than 0. What will change? X is greater than 0, y is greater than 0. What will change in our case? What will change in first order conditions? We have discussed it some weeks ago, I think 3 or 4 weeks ago, we have discussed, or maybe more, because it was even before linear programming. Yeah, maybe 4 weeks before. Yeah, that was a long time ago. Who remembers?
It's something about the x1, x2, and x3.
Yeah, it's x times dl dx is 0, y times dl dy is 0, and we have more inequalities but less variables. So the case B is, who remembers what should be the sign dl dx and dl dy?
All positive.
Sorry?
It's all positive, right?
No. If you look at this expression, no, let's a, oh, I have a there everywhere. Okay, so what is dl? So what will be the difference? Dl dy is, so what is the link between them? If I will take the dl full dy, the difference will be only in one term. So it's exactly dlb with respect to dy plus lambda 2. So if you pay attention at the difference of two approaches, and that's basically the proof, this is the difference. And if that one should be 0, and if lambda 2 is positive or 0, then dl with short, in a short version, should be non-positive. If the sum of two values is 0 and one of them is non-negative, the other one should be non-positive. Okay, yeah, let's continue.
Yeah, let's do it.
We can't hear you, Boris Borisovich.
Hello, Boris, we can hear you. Something happened by microphone. It's stuck for a while. Yeah, I still can hear you. It's muted.
Everything is fine.
Yeah, this is fine. This time is fine.
Okay, we have written two approaches, but I will solve that one. Why I will solve that, the approach B, because I have less lambdas, but the solution is the same. Okay, let's write everything. Let's write everything we need. Sorry, we have not enough place, but let's. Okay, lambda should be non-negative, x should be non-negative, y should be non-negative. 2x minus 2x squared minus 2y minus 2y squared should be non-negative. What else should I write? I should write lambda times 2x minus 2x squared minus 2y minus 2y squared is 0. What should I write more? I should write more that x times dl with respect to dx is what? dl with respect to dx, I think it's 1, it is it is it is oh, I need to maximize it. Okay. Okay, I have 1 plus lambda times what will be the derivative. So this is x times dl dx is 0. I have 2 minus 4x is 0. Yeah. Y times dl dy is 0. So y times 1 plus lambda plus minus 2 minus 4y is 0. And I have two more inequalities. dl dx is non-positive, dl dy non-positive. So it's 1 plus lambda, sorry, it is 1 plus lambda times 2 minus 4x is non-positive. 1 plus lambda minus 2 minus 4y is non-positive. Ooh, I have a lot of things to do, but I'm brave enough. I have 5 minutes. And I think that's enough. Okay, that's first of the conditions applied to our problem. Okay.
Sorry, 1 minute.
Yeah.
Could you give some comment for the functions in here?
Sorry?
Some little explanation for the functions in here.
I don't see you. I don't understand the question. Could you write it?
Sorry, can you give me a little explanation for the functions in here?
A little explanation for what?
Yeah, or comments for the functions, the flow of the functions in here, because
It's lambda times dl d lambda is 0. That is these are my constraints. This is the first of the condition from Lagrange multiplier with inequality constraint.
okay.
What do you mean by comments? So these are comments. Why do I have these inequalities?
Fine, thank you.
Okay, let's solve them very fast. As lambda is non-positive, so these are the most, I think, productive inequalities. So I get this one, 1 plus lambda is non-zero. That one is non-zero. Yeah. So this is non-zero. This is non-zero. Y is 0. Yeah. I get y is 0. Okay, I'm happy. I plug in everywhere y is 0. So I have two subcases. So this is the most useful. This is the most useful. Then I have here x. I have two subcases. Case A, x is 0. Case B, x is 2. Okay. So let's at the point x0, y0, I don't need even to check it because I know that even it's okay with first order condition, so I will need to check it separately. So I have two suspicious points. Okay, let's check that everything is okay for the case B. So warning,
Maybe
0, 0 is a bad point.
equal to 1/2.
1/2, y 1/2. Ah, yeah, obviously, yeah. Thank you for being, thank you. Yeah, 2 minus 4x equals to 0 when x is equal to 1/2. Yeah, it's my fault. Yeah, you are right. Be brave because I can make arithmetics. That's possible. Yeah, you're right. Okay, so 0, 0 is a bad point and this is not satisfied. We will need to check it separately. So even if all conditions are satisfied, even if something fails, we need to check it separately. Okay, so it's suspicious point in any case, suspicious point in any case. The point 1/2, 0. Let's check that everything is satisfied. So lambda should be 0. Yeah, I may, so y is 0, x is 1/2. So I make a conclusion that lambda is 0. If lambda is 0, that is okay. 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 Everything is fine. Yeah. Okay, everything is satisfied. So I have second suspicious point. Bingo. Yeah, everything is fine.
It's okay.
Yeah, I think everything is fine. Yeah. Yeah. Okay, so what are my conclusions? My conclusions are I have two suspicious points. One was suspicious even before Lagrange multiplier method. Yeah. One point was suspicious when we have checked in DCQ. The second point is suspicious because it satisfies first order condition. So maybe the maximum is there, maybe the maximum is there. Okay. Let's check sufficiency conditions. Sufficiency. We have our constraint is 2x minus 2x squared minus 2y minus 2y squared is non-negative. So my function f is continuous. This feasible set is the feasible set is I'd like to use Weierstrass theorem. Obviously, I will not do it with Hess matrix. My function is continuous. My feasible set is bounded and bounded and closed. So it's compact set. So I may draw it. So we can easily draw it. Yeah, do not forget. We can draw the feasible set. It's non-linear, but that's fine. We have two variables. Don't be shy. X is non-negative, y is non-negative. So if you'd like to draw it, so it is x minus x squared minus y squared equals to 0. What should I do? I think something like I will add. I think add 1/4. Yeah, it's 1/2 equals to minus 1/2. It's equals to minus 1/4 plus x minus x squared minus 1/4 minus y squared. And I see that is minus 1/2 equals to minus x minus 1/2 squared minus y plus 1/2 squared. And basically it's a shifted circle. X minus 1/2 squared plus y plus 1/2 squared is less than 1/2. And basically I have a circle with the center 1/2 minus 1 over 2. Yeah. So if I'm not mistaken with the sign, I have a circle like that. And my region where profit is positive is very small. So this is a feasible set. Yeah. Okay. Any question?
Yeah, I have a question about this. So the way we calculate the area in this part is by
I
using.
have not calculated area. I have not calculated area. There are no, so I have just taken the last inequality. I have divided it by 2. I have multiplied it by -1, so I get x squared minus x plus y squared minus y is less than 0. I have added plus 1 over 2 to both sides. Y squared minus y plus 1 over 4. I have added plus 1 over 2 to both sides. And I have completed the squares, x minus 1 over 2 squared plus 1. Sorry, that is plus. Yeah. Plus 1 over 2 squared is, so I see that it's a circle. I have not calculated the area at all. No. Okay. So
Okay.
basically, I see that the feasible region, this small part of a circle, is compact because it's bounded and closed. So Weierstrass theorem is applicable, and it says a function should have their global maximum. So Weierstrass theorem, the function should have a global maximum on the feasible set, but I have only 2 suspicious points. So I can just check which one is better, because Weierstrass theorem says me, oh, there should be a maximum. And I have only 2 suspicious points. So I will just check them. F at 0, 0 is 0. F at 1 over 2, 0 is that is my function f, and it is I think better. Yeah, it's 1 minus 1 minus 1 over 2. It's 1 over 2. Woohoo! The second one is better. So the final answer is I have 2 suspicious points. With at 1, the value of the function is 0. At the second, the value of the function is 1 over 2. I'm maximizing. So the final answer is 1 over 2, 0, and maximal value is 1 over 2. Here it is. This is the best point. Okay, any questions?
I want to know if in the function before the calculation 0.0 is not a suspicious point. How do we approach the answer? Using the same method but with different numbers or something?
Sorry, 0, 0 is suspicious point. Is a suspicious point because IndCQ is violated. So even from IndCQ, we can see that it's a suspicious point. We should check it separately, but we have checked it.
Oh, so the only difference is to check this point.
Yeah,
Is
check that point. So when IndCQ fails, don't be scared. Just check separately this point. What happens there?
Yes, thank you.
Okay, that's all for today. Next time, I hope we will cover duality in a general context, not only in linear programming, because it's useful in modern machine learning approach. So that the duality plays important role in optimization problems. And basically every machine learning problem is an optimization problem. If you have any questions, just don't be shy to send me them beforehand. I will spend less time on inventing examples to your answers. Thank you for listening
Sorry,
to my
Boris.
lecture.
I want to ask, if I want to contract you, which one is the best method? Use WhatsApp, or email, or which?
Sorry?
I mean, if I want to contract you, which one is the best method? Are you in WhatsApp? Will you contact you?
You can contact me anyway. I'm not hiding. You have, so if you go on the website of High School of Economics, you have my email, my mobile phone. You can contact me. So I'm saying I'm not a person hard to contact. So you have a lot of options to contact me by email, by WhatsApp, by Telegram, by phone. Okay. I'm not hiding. I'm not criminal. So I'm happy.
Me too.
Okay. Have a nice evening.
Nice evening. Nice
Thank you,
day.
Boris
Good night.
Борисович. До свидания.
Thank you. Goodbye.
Bye, Boris.
Bye-bye.